In this video, I'm going to run through the P1B GCSE Physics pre-exam PowerPoint. P1B is broken down into two components, P1.4 and P1.5. I'm going to start with P1.4, which is methods of generating electricity. When we're generating electricity, we can classify resources into two groups, renewable and non-renewable. Renewable energy resources can be replaced or regenerated and will never run out, at least not for a very long time. And examples of renewable energy resources include wind and solar. Non-renewable energy resources will eventually run out, and once they're used, they cannot be used again. Examples of non-renewable energy resources include coal and oil, or other fossil fuels. The reason they're non-renewable is it takes them millions of years to form. On this slide, we see a number of energy sources that you need to know about for your exam. The energy sources are solar, fossil fuels, nuclear fission, biomass, geothermal, wind, wave, hydroelectric and tidal. For each of these sources, you need to know how they produce electricity, but you also need to be aware of the advantages and disadvantages for the sources. When we discuss the advantages and disadvantages, you need to know about their environmental impact, the economical impact, the cost, whether they can meet supply or demand, their efficiency and their reliability. In terms of how each of the methods of generating electricity produce electricity itself, solar power stations do not require a turbine. Solar cells tend to work by a light photon striking the surface of the solar cell, and that releases electrons, which is electrical current that flows. So you can see that solar are no turbines. Fossil fuels, nuclear fission and biomass are all what we call thermal turbines, or thermal power stations. And thermal power stations work because the thermal power stations heat up water first, the water turns to steam, the steam turns the turbine, and the turbine drives a generator. The ones along the bottom here, so you've got wind, wave, hydroelectric and tidal, they're all examples of direct turbines. So they turn the turbine directly, they turn the turbine either using the energy from the wind or the energy of moving water, and that turbine is turned, the turbine then drives the generator, and the generator produces electricity. So they're called direct. Now, the geothermal could potentially go either way. So you can either use hot rocks to heat up water, which will then produce steam and then drive a turbine, so that will be a thermal power station, or you can pump steam directly out of the ground and turn the turbine directly, and that will be a direct power station. As I said at the beginning of the PowerPoint, you need to be aware of the advantages and disadvantages for each type of method of generating electricity. Now, unfortunately in this PowerPoint I won't have enough time to discuss each advantage and each disadvantage for every single source, but what I have done is I've made one advantage and one disadvantage for all the methods of generating electricity that you need to know about. So if we start off with solar, the main advantage of solar is it can be used in remote locations. So it doesn't need to be connected to the national grid, and it can produce electricity in remote locations where you haven't got the cables and wires of the national grid leading to. The main disadvantage of solar is that it's not reliable because the electrical output depends on the weather. So if you've got a cloudy day or at night time, the amount of electricity that's being produced is either zero or reduced from its maximum. If we move on to fossil fuels now, fossil fuels are a really reliable source of energy. That's probably the main advantage, is that they'll always be able to meet demand. Things like gas have got a quick startup time, so they can meet surging demand as well. So they're a really reliable source for producing electricity. However, they do produce greenhouse gases, and that's probably their main disadvantage, is the pollutants that they release. So when you burn fossil fuels, they produce carbon dioxide. Carbon dioxide contributes to global warming because it's a greenhouse gas. And they also release other pollutants that can produce things like acid rain. Moving on to nuclear fission next. So nuclear fission again is a really reliable source of energy. It also produces the most energy per kilogram of any method of generating electricity. The main issue with nuclear is the fact that it produces nuclear waste, and it's got radioactive waste that will last thousands of years, and you need a way of storing that, which is the main drawback to nuclear. So moving on now to biomass. Biomass is a good method of generating electricity because it's carbon neutral. So biomass is basically where you grow crops and then you burn them to produce electricity, obviously by heating the water to turn the turbine to drive the generator. And biomass is carbon neutral because the carbon dioxide that's released when you burn biomass is equal to the carbon dioxide that's taken out of the atmosphere when you grow the plant in the first place. The main drawback to biomass is that you need a large amount of land for production, and it will also reduce other things in terms of like agriculture. So farmers that would traditionally grow crops for food won't be able to grow them because they're growing crops for biomass instead to produce electricity. It really is a large amount of land that's required. Looking on to geothermal next. Geothermal is possibly one of the best of the renewable energy sources, mainly because it's got no fuel costs. The main drawback to geothermal, it's also reliable as well, but the main drawback to geothermal is that it's only available in some areas. So you need volcanic activity to be able to use geothermal, and obviously in the place like the UK, there is no volcanic activity, and therefore geothermal is not an option to be used in the UK. If we move on to wind now, wind power is really good because you've got no pollution. Okay, it's a renewable source as well, but the main drawback to wind is, again, it's not reliable. It depends on the weather, and if it's not windy, then the amount of electricity you're producing is going to be low, and if it's a really windy day, sometimes you have to shut the wind turbine down so you don't damage it. So next we're going to look at wave energy. Wave energy is really good because there's no fuel costs, it doesn't cost you anything to run, but it is a problem because it does damage habitats for sea life. So now we're going to look at hydroelectric, which is here. Hydroelectric is really good because it's reliable. It's the most reliable of all the water and wind methods of generating electricity, especially pumped storage. So pumped storage is where you use electricity that's generated at night when you've got low demand to pump the water back up to the top reservoir to be released back down to the bottom reservoir and turn the turbines in the morning or when you need it. It's really reliable. You can turn it on very quickly. It's got a quick startup time. The only drawback to hydroelectric is that it damages habitats, and obviously you also need a hillside to be able to use it. The final method that we're going to look at is tidal. Tidal is good because it's reliable, and there's also no fuel cost involved in tidal as well. But it's difficult because it damages habitats, and it's not good if the local economy depends on the sea. So usually tidal has to be built across an estuary or a river mouth, and when you do that, it stops boats in some cases getting out to sea, and it also, some people consider that to be a bit of an eyesore, and so it gives you visual pollution. It's worth pointing out that there are more advantages and disadvantages for each of these types, but I just don't have time to go into it now. So when we generate electricity, if we're looking at a thermal power station, how we generate electricity is we start off by heating up the water. With fossil fuels, we do that in a boiler. Biomass, it would be a boiler as well. Whereas in a power station, a nuclear power station with nuclear fission, it would be a nuclear reactor that's producing the heat. The water is boiled and turned into steam. The steam will come along here and dry and turn these turbines. These turbines will then drive the generator that will spin round, and the generator will send electricity or produce electricity, which will get passed on to the national grid and eventually comes to our homes. The steam that is used to turn the turbines will go up into the cooling towers, where it will cool back down into water, and that water will be reused in the boiler there. In terms of the energy transfers that take place, we've obviously got thermal energy being in the boiler, being used to produce kinetic energy, it's the steam and the turning turbines, and then the movement of the generator will produce electrical energy. So just having a little look at how we can produce electricity using water. So the first method we're going to look at is waves, and waves can be used as a wave moves past the turbine, it can turn the turbine directly, and that will produce electrical energy as the turbine spins. That will then drive a generator. The generator produces electricity, and we'll have cables under the seabed here going back to the national grid. So the next method of generating electricity using water is hydroelectric power. So here you've got a reservoir at the top and a reservoir at the bottom. What you want to do when you want to produce electricity here is you open this gate, and the water will flow down here and going past the turbine. The turbine will turn. That will then drive the generator. The generator produces electricity, and the electricity is then gone to a transformer where it will be stepped up to go to the national grid. Okay, and what we've got is we've got gravitational potential energy at the top with the water, and it turns into kinetic energy as it falls down here, and that kinetic energy is then used to turn the turbine. And as I mentioned before, you can have a pumped storage system where in the night time when you've got low demand for energy, you can pump the water back up to the top, so you've got an endless supply. Finally, we'll look at tidal barrages. So tidal barrages, how they work is that you have the water coming in, so the tide will come in, it will go past this, through these gates, on its way in it will turn the turbine, or sometimes it will go over the road, and you can then store it behind your tidal barrage. When you want water, you can lift up these gates, and the water will flow back out towards the sea, and as it does, it will turn the turbine, which will then drive a generator, and that will produce electricity. How direct turbines work is that they produce electricity by using kinetic energy, which goes into electrical energy. So they spin the turbine directly using water, or in the case of wind, it's just the wind that turns the turbine, and that then drives a generator, and the generator produces electrical energy. Just looking at the difference between solar cells and solar panels. So solar cells, they convert light energy they receive from the sun into electricity, and the way they do that is the light energy causes electrons in the material to be released, and that they flow as the electrical current. Or solar panels are slightly different. They're what people tend to have on their houses, and they use light energy they receive from the sun to heat water, and then that can go into your boiler and produce hot water for the household. So now we're going to have a look at carbon capture and storage. Carbon capture and storage can be used to stop carbon dioxide emissions. So old oil and gas fields could be used for storage, and the idea is that when you burn fossil fuels, the carbon dioxide that's released is not pumped out into the atmosphere, but it goes through a pipe and that is then stored in underground, reducing the amount of carbon dioxide that we're pumping into the atmosphere. And that will also reduce the effects of global warming. Carbon neutral is another key term that you need to know. So some fuels are carbon neutral, and that is again the idea that the carbon dioxide released when they are burned is equal to the carbon dioxide absorbed as the fuel is formed. Examples of these fuels include all biofuels such as ethanol from fermenting sugar canes, wood chips and straw. We're just going to have a look at the national grid. So how national grids work is that you start off with a power station, and that produces electricity in one of the ways that we've seen beforehand. Once the electricity has been produced, that will then go to a step-up transformer. The job of the step-up transformer is to increase the voltage, so you get a high voltage supply, and reduce the current, so that will then go through the pylons across the national grid until it reaches a step-down transformer. And the job of the step-down transformer is to reduce the voltage and increase the current so it's safe for our homes. This works on the principle of power is equal to current times voltage, which is shown here. So if I want to increase my current, I need to decrease my voltage to get the same power. So power remains constant and current and voltage will change. Remember that the step-up transformer is there to increase the voltage, so it will increase voltage and as a result reduce the current. The reason it does that is so that it's more efficient when we transfer the electrical energy through the pylons in the national grid. The reason it's more efficient is by having a higher voltage and a lower current. What that means is there's less electrons in the wire. If there's less electrons flowing in a given time, there's going to be less collisions, so less energy is then wasted as heat energy in the national grid. And that brings us to the end of P1.4 for this PowerPoint. So we're going to move on now to P1.5, which is all about waves. I hope you enjoy. So a wave is a means of transferring energy from one point to another without there being any transfer of any substance between the 2 points. The wavelength, which is highlighted here, is the distance between one wave peak and the next wave peak along the path of a wave. And wavelength is measured in meters. Other key terminology that you need to be aware of for waves is frequency, and the frequency is the number of wave peaks that pass a point in 1 second. Frequency is measured in hertz. Now if I was to change the scale rather than looking here at wavelength, so it must be a distance, if I change it to look at time in seconds, what I will be able to work out is that my wavelength would also be equivalent to my time period, which is capital T. And you need to be aware that time period is equal to 1 over frequency. Time period is measured in seconds. It's the same distance as my wavelength, but it's only if it's showing a time base along the bottom. And you're not given that equation on the exam, so you need to learn that one. So time period is equal to 1 over frequency. Wave speed can be calculated using speed equals frequency times wavelength. Remember the symbols for these are that wave speed is v equal to f for frequency times wavelength, which is lambda. You will be given that. So we're going to briefly look at the electromagnetic spectrum here. The one that you'll be most familiar with is visible light. Okay, and you'll know that visible light can be broken down to a spectrum of colours, which go red, orange, yellow, green, blue, indigo, and violet. And within there, that basically is a spectrum of light, as we call it, and those combined make up white light. But what we now know is that there are other versions of light that we just can't see. The other versions of light are displayed in the electromagnetic spectrum. Within the electromagnetic spectrum, all the energies and frequencies are proportional to one another. At the top here, we've got gamma rays, and they have the highest energy and frequency but the shortest wavelength. At the bottom we have radio waves, and they've got the lowest energy and frequency but they've got the longest wavelength. As we go up, we can see radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Some people have different ways of remembering them. Hopefully you've seen the YouTube video about the electromagnetic spectrum song. It's really worth a watch in terms of a method of learning these waves. But also you can remember them as real Martians invade London. For visible light, we have to remember the L, using X-ray guns. You also need to be aware that EM waves can be used for communication, where radio waves are used in TV and radio signals. Microwaves are used in mobile phones and satellite TV. Infrared radiation is used in remote controls, and visible light is used in photography. So just a reminder about the things that the EM spectrum have in common. So all electromagnetic waves, including visible light, travel at the same speed through a vacuum. They're all transverse waves, which we're going to look at in a moment, and they all have an electric and magnetic field oscillating at right angles to the direction they travel in. The speed of light in a vacuum is 300 million meters per second. There's a few effects that you need to be aware of about waves. The first one we'll look at is diffraction. Diffraction occurs when a wave spreads out from a gap or bends around an obstacle. Diffraction is more significant with low frequency at long wavelengths, and diffraction results in the energy of the wave spreading out. And for a wave to diffract through a gap, the wavelength should be a similar order of magnitude to the gap size. So you can see here that the wavelength before is around that distance there is about this, which is why we've got a nice curving effect afterwards. When you draw them, you need to try and make sure that the distance there we call lambda, which is a wavelength, and that's the same as that distance there, which is also lambda. If you've got a larger gap size, like this, I've got the same sort of waves going in, the effects of spreading out is somewhat less. So they would look more straight with slight curves at the edges there. Another thing you need to be aware about waves is that they will reflect. The law of reflection is that the angle of incidence is equal to the angle of reflection, and you should make sure that both angles are the same here, and then measured to the norm, which is this dotted line. So the normal is a perpendicular line to the mirror, so you see that's a right angle there. It's a mirror for my normal, and what we do is we measure the angle from the normal to the ray. So the incident ray comes in here, it bounces off, and that's a reflected ray, and the angle of reflection is equal, it's the same size as the angle of incidence, and you should probably use a protractor to make sure of that in the exam. The next bit we're going to look at is how we form images by a plane mirror. So you can see here, you might be asked to do this in the exam. So you can see that if we take our object here, which is RL, we've drawn a line coming here and drawn the reflected line on and extrapolated this back in the mirror to see where it would come from. And we've done the same with the blue line. Remember, the angles should be the same. The angle of incidence should be equal to the angle of reflection. And we extrapolated this one back, and then we can draw our image there. These are construction lines, so that's not really where the light ray comes from, but it's where we see the light ray coming from if we look into the mirror. So we'd imagine that the object would be inside the mirror. You need to be aware that the image produced by a plane mirror is the same size as the object. It's the same distance behind the mirror as the object is in front of it. It's upright, so it's the same way vertically, but it's back to front compared to the object, so it's laterally inverted. And it's a virtual image. It doesn't really exist. You can't project it onto a screen, but you can see it inside the mirror. Just to clarify a few things, so real images are formed where the actual light rays cross, where real light rays cross, so you can project it onto something. So real images can be cast onto a screen. An example of that is a projector image. Whereas virtual images are formed when light rays only appear to come from. So they're not real. It's where we see the light rays coming from when they come off of something like a mirror or through a lens, but it's not actually where the image is. And examples of that include images by a plane mirror. So now we're going to look at refraction. Refraction occurs when a wave changes speed as it passes from one object or region to another. This speed change usually causes the waves to change direction, as you can see here. So we've got the waves coming in like this, and now we've got them changing direction as they bend. Water waves slow down as they pass over from a deeper to a shallower region, and light slows down as it passes from air into glass or perspex of water. The reason it slows down as it goes from air to glass or perspex is because the density of glass or perspex is greater than the density of air, and therefore causes a light ray to slow down. And when it slows down, it will bend towards the normal. When it speeds up, when the water wave speeds up or the light wave speeds up, it will bend away from the normal. So now we'll just have a look at the difference between transverse and longitudinal waves. The first waves that we're going to look at are transverse waves, and for transverse waves, their displacement, so the direction of the particles moving, is at right angles to the direction of propagation of the wave. So if you imagine looking at this diagram that we've got here, you can see we've got like a sine graph. What's actually happening is that the waves are moving that way, the energy is being transferred in that direction, but the particles move up and down here. So you can see that's a right angle between the two. Examples of transverse waves are electromagnetic waves, so light, and all other waves in the electromagnetic spectrum. Further examples include water waves, that you see at the seaside. If we look at longitudinal waves now, you can see here that longitudinal waves, the displacement of the particles is parallel to the direction the wave travels in. So the wave will move in this direction, and the particles will oscillate around a point. So they will oscillate in two directions like so, and you can see that that direction is in the same direction that the energy is transferred and the direction of wave movement. Examples of longitudinal waves include sound waves. Examples of longitudinal waves include primary seismic waves, whereas you need to remember that secondary seismic waves are transverse. So we're going to look at sound now. Sound waves are longitudinal waves which can cause vibrations in a medium, which can then be detected as sound. Now remember that sound waves are longitudinal, but sometimes it's useful to represent a sound wave as a transverse wave. The reason we do this is that transverse waves are often easier to read because the information they contain is easier to see. So first of all, we're going to look at how loudness increases with amplitude. So if you imagine we've got an amplitude here, so draw on the equilibrium position. The amplitude is between the top line and the equilibrium position. So there's the amplitude of that wave. If we look at this one, draw on the equilibrium position, the amplitude would be that size there. So you can see that the louder sound has a larger amplitude. So that means that the loudness of a sound increases with the amplitude. The first wave here has a relatively quiet sound, whereas this one has a much louder sound because the amplitude is greater. Now what we're going to look at is the pitch of the noise that's produced by a sound wave. The next property of sound waves that we're going to look at is their pitch. Now the pitch of a sound wave depends on its frequency. Pitch depends on frequency, frequency depends on wavelength. Now looking at the wavelengths of the two waves, we can see that the wavelength of the red wave is much larger than the wavelength of the blue wave. This means that the red wave has got a higher wavelength and therefore a lower frequency. We can see that by viewing that there's less waves in a given time, whereas the blue wave has got a smaller wavelength and therefore a higher frequency. Because the blue wave has got a high frequency, that means it will have a high pitch compared to the red wave, which has got a lower frequency and therefore has a low pitch. So now I'm going to look at the Doppler effect. So what we've got here is we've got a moving ambulance, which is this bit here, and the ambulance is moving, but as it moves it emits a circle of sound. Okay, so the circle you can see at A. As it moves forward to part B, it emits itself another circle of sound, which is this one, but you can see that it's moved in the direction going this way. That means that as the ambulance continues to move, it emits sound always as a circle, but the sound waves at the front get bunched together. And you can see that their wavelength at the front becomes reduced. The distance between the waves becomes reduced. So they get a smaller wavelength, but an increase in frequency. If we look at the back of the ambulance now, because they're moving away from each other, you can see that we actually end up getting an increase in wavelength. The wavelength gets greater. Because the waves are getting stretched out, so you get an increase in wavelength and a decrease in frequency. So as the ambulance moves towards us, because the waves get compressed and we get an increase in frequency, the ambulance actually sounds more high pitch as it travels towards us. whereas when it passes us and is driving away from us, the sound waves become more stretched out. That increases their wavelength, decreasing their frequency, so the ambulance will now sound to be more low pitch. So the Doppler effect just basically summarises that if something's travelling towards us, then the wavelength will decrease and the frequency will increase. If something's travelling away from us, then the wavelength will increase and the frequency will decrease. This idea can then be applied to spectra that we receive from stars. So if we look at the top image, we can see this is an unshifted spectra received from a star. Below this is actually what we do receive from distant galaxies and the light coming from them. And what you should notice is that these spectral lines have all been shifted towards the red end of the spectrum. So if you imagine that line should have been there, but it's actually been moved slightly in that direction. So we call that redshifted. Now there are actually two types of this spectral change that we can see in stars. The first one that we can sometimes see is something known as blue shift. And blue shift occurs when we get a decrease in wavelength and an increase in frequency. So a light wave is moving towards us, and that makes the light from that star appear to be bluer, and that's known as blue shift. The more common type that we see in space is actually known as redshift. And this is when we get an increase in wavelength and a decrease in frequency, as shown here. Okay, and that makes the light redder and is known as redshift, and that means that the star or the galaxy in question is moving away from the Earth. So this was really important because in 1929 Edwin Hubble discovered that the light from distant galaxies was redshifted. He found that the redshift was proportional to the distance to a distant galaxy. Therefore, the more distant a galaxy is away from us, the faster it is moving away from us. So this information basically explains that everything and all the distant galaxies are moving away from us, but those that are the furthest away are actually moving away from us the fastest. So Hubble's observations tell us that distant galaxies are receding from us, and the further away they are, the faster they are moving away from us. So if we go into the future, what we'd expect to see is those galaxies getting further and further and further away from us. That also means that if we go back into the past, those galaxies will have been closer to us than they are now. And if you keep extrapolating backwards and saying, well, where were they like 100 years ago, or 1,000 years ago, or 2,000 years ago, it would always be getting closer. This led to the idea that at some point in the past, all the matter in the universe must have been together in one point, and then something must have changed so the universe began to expand, and that theory was known as the Big Bang Theory. Now the Big Bang Theory is an explanation of the origin of the universe, and it states that the whole universe was in a very small, hot, dense point. Then nearly 13.5 billion years ago, or 13,500 million years ago, expansion started, and the universe has continued to expand ever since. But it did originate from a very small initial point that was very hot, very dense. There's some sort of explosion that caused the universe to expand. In science, we can't accept a theory until we've got enough evidence to support it. The Big Bang Theory has got the following pieces of evidence. So the first one is that the light from other galaxies is redshifted. This is supported by the Big Bang Theory because that means that other galaxies are moving away from us. The second piece of evidence is that the further away a galaxy is, the more its light is redshifted. This supports the Big Bang Theory because that basically means that the whole universe is expanding. And that supports the idea that at the start, the whole universe was in a single point and could have originated from a single explosion. The final piece of evidence is the cosmic microwave background radiation, or CMBR, exists. CMBR is a relatively uniform background radiation that can be detected anywhere in the universe, and it is the remains of the energy created just after the Big Bang. The fact that CMBR exists means that at one point the universe must have been very hot because it had generated lots of energy in its explosion and has since cooled down to form the CMBR that exists everywhere in the universe now. On the last slide, I would just like to spend a bit of time running through the physics equation sheet. On the physics equation sheet, you're given the equations you'll need for the exam. I've already mentioned that one of the equations, which is that F equals 1 over t, so frequency equals 1 over time period, is not given to you. But the rest of the equations are given to you for this exam. If you're doing the Unit 1 paper, you'll need all the equations, whereas if you're doing the Unit 1b paper, you'll probably only need velocity is frequency times wavelength. I've also included the equation triangles. Notice that you won't be given these in the exam, but they're there for you to use if you would like to write them down now and then try and remember them for your exam. I'd like to wish you the best of luck in your physics exam, and say thank you very much for watching this video. Goodbye.